Picture a huge underground car park with no map. You know where you're standing, and you know the car you want. But all you can do is walk. Take whatever turning appears, and back up if it leads nowhere. This is uninformed search, blind search. The algorithm has no sense of which way the goal lies. No compass, no distance estimate. It knows only the map's raw structure, which state connects to which, and nothing more. The whole question is simply, in what order do you explore? Four classic answers. Breadth first search fans out level by level. Depth first search plunges down one path. Uniform cost search follows the cheapest total cost. And iterative deepening blends the best of the first two. They all share one language. The frontier. The nodes we've reached but not yet explored. The explored set. Nodes already done. Expanding a node just means generating its neighbors. What separates the four is one thing only. Which node leaves the frontier next? Start with breadth first search. Its instinct is patience. Explore every node at the current depth before going one step deeper. Level 0, then level 1, then level 2. The data structure that gives you that is a first in, first out queue. Whatever you add first, you take out first. New nodes join the back. The next node to explore always comes off the front. We seed the frontier with the start, S. Take S off the front and expand it. Its neighbors A and B join the back of the queue. That's level 1, both waiting. First in, first out. So A comes off before B. Expand A. Its children C and D go to the back, behind B. The queue is now B, then C, then D. Notice, B still waits its turn, even though A's children arrived later. Now B comes off the front. Expand it. And its neighbor is the goal, G. The very first time breadth first search reaches the goal, it does so by the fewest possible edges. Here that's just 2, S, B, G. That guarantee is what makes BFS shine. It is complete. If a solution exists at any finite depth, it will find one. And for equal step costs, that shallowest solution is also the optimal one. But there's a price. To reach depth D, BFS may generate every node above it. 1 plus B squared all the way up, which is order B to the power D. That's the time. The catch is the memory. Because a whole level of the tree waits in the queue at once, the space is also order B to the D. Exponential memory. On any real problem, that is what kills breadth first search long before time does. Depth first search has the opposite temperament. Impatient. It commits to one path and drives as deep as it can, only backtracking when it hits a dead end. Same map, a very different walk. Swap the queue for a stack. Last in, first out. The most recently added node is the very next one you explore. That single change turns patient breadth into headlong depth. Push the start, S pop it, and push its children, B first. Then A, so A ends up on top. The stack now reads B underneath, A on top. And A is what we grab next. Pop A. Push its children C and D, so C sits on top. Look what happened. B is buried at the bottom, forgotten for now. Depth first search has already abandoned the right side of the map to chase the left. Pop C. Its neighbor is the goal. G. Reached along S. C, G. 3 edges deep. Depth first search found a path, and it found it fast. But notice, it is a longer route than breadth first's 2-edge answer. So depth first search is not optimal. The first goal it meets can be deep and expensive. And on an infinitely deep tree with no limit, it can chase one branch forever and never come back. So it isn't even complete. But depth first search has one magnificent virtue: memory. At any moment, it only needs to remember the single path it's on. plus the untried siblings along the way. That's order B times M, where M is the deepest the tree goes. Compare that to breadth first's B to the D. Linear versus exponential. That is a colossal saving, and it's exactly the strength we'll want to rescue later once we fix the completeness problem. Let's freeze that contrast. Same graph, same start, same goal, but breadth first and depth first walk it in a completely different order and come away with a completely different path. Breadth first, on the left, expands S, then A, then B, patiently across the level, and takes the two-edge path S, B, G. Fewest edges, but those edges happen to be heavy, so the total cost is 10. Depth first, on the right, expands S, then A, then C diving down the left spine, and takes the three-edge path S, A, C, G. More edges, but those edges are light. Its total cost is only 3. And here's the twist that sets up everything to come. The fewest edges path costs 10. The longer path costs 3. So on this graph, fewest edges is not cheapest, which means neither strategy is minding the cost at all. That is the gap the next algorithm fills. Uniform cost search fixes exactly that. It stops counting edges and starts counting cost. For every node, it tracks g of n, the total path cost from the start to that node, and it swaps the queue for a priority, q, a min-heap keyed by g. It always pulls out the node with the smallest path cost so far, not the shallowest one. Everything else is the same three-step loop. Pop the cheapest, test for the goal, expand, and update each child's g. One subtle, beautiful detail. Unlike breadth first, uniform cost search does not stop the moment it generates the goal. It waits until the goal is actually popped, the cheapest thing in the whole frontier. Only then is it certain no cheaper route can still be hiding. This is Dijkstra's algorithm, wearing its search theory clothes, and it buys you the strongest guarantee yet. As long as every step cost is non-negative, uniform cost search is optimal for any costs at all, not just equal ones. Let me show you uniform cost search catching a mistake breadth first can't. A tiny graph. From the start S, two ways to the goal G. Through the first hop costs 1, but the second is a brutal 10. Through B, both hops cost 2, so the two paths cost 11 and 4. Breadth first search only sees depth. Both routes reach G in two edges. And since it tries A before B, it returns S, A, G, and stops. Cost 11. It grabbed the fewest edges and walked straight into the expensive path. Now watch uniform cost search. Pop S at 0. It sets G of A to 1 and G of B to 2. Smallest is A. So pop A next, and it reaches G with cost 11. But here's the discipline. It does not stop. 11 is not yet the cheapest thing in the queue. Pop B at 2. From B, the goal costs just 2 plus 2. 4 cheaper than 11. So it keeps the 4 and drops the 11. Now G sits in the queue at 4, the smallest thing left. Pop it. That's the goal. And its cost is provably minimal. 4, not 11. Uniform cost search found the genuinely cheapest path, S, B, G, exactly where breadth first failed. Same graph, and the algorithm that watches cost wins. We're left with a frustration. Breadth first is complete and optimal, but drowns in memory. Depth first sips memory, but can wander off forever. Can we get one algorithm with the completeness of the first and the thrift of the second? The bridge is a small idea. Depth-limited search. Run depth first, but forbid it from ever going below a chosen depth limit. L? It can't run away. But if the goal sits below L, it'll miss it entirely. Pick L too small, and you fail. Iterative deepening is the masterstroke. Don't guess L. Sweep it. Run depth-limited search with L equals 0. No goal? Restart from scratch with L equals 1. Then 2, then 3, growing the limit until the goal appears. Because each round explores every node down to its limit, the depths come out in order 0, 1, 2, all the way to D. So iterative deepening inherits breadth first's prizes. It's complete and optimal for equal costs. Yet its memory is depth first's, order B times D, the best of both. But wait, doesn't restarting from the top waste effort? The shallow nodes get re-expanded every single round. It sounds wasteful. Let's actually count it. For a branching factor of 2 and a goal at depth 2, the route is expanded 3 times, once per round. Depth 1 nodes, twice. The deepest nodes, only once. Add it up. 11 expansions against breadth first 7. The deep level, the biggest one, is still only touched once. Just a 50% overhead here, and it shrinks as the tree fattens. For a branching factor of 10, iterative deepening does barely 11% more work than breadth first. The deep nodes always dominate the count. So the time is still order B to the D, and you paid almost nothing to slash the memory. Time to put all 4 on one card. 4 questions decide everything. Is it complete? Is it optimal? How much time? How much memory? Breadth first. Complete and optimal when the costs are equal. That's the little star. But time and memory both blow up to B to the D. Depth first. Not complete without a limit. That's the dagger. And never guaranteed optimal. But its memory is a beautiful order B times M. Linear in the depth. Uniform cost. Complete and genuinely optimal for any non-negative costs. Its time and space are worst-case exponential, on the same scale as breadth first. An iterative deepening. Complete, optimal for equal costs. Again the star, with breadth first time, B to the D, but depth first tiny memory, order B times D. That last row is the sweet spot. Read the star and the dagger as the fine print, equal costs for optimality, and a depth limit for depth first's completeness. Everything else you need to choose a blind search lives on this one card. Your turn. Here's our very first graph again. Weights and all S to a 1, A to C1, C2G1, and the shortcuts S to B5, B to G5, A to D4. Run uniform cost search from S. What is the cheapest cost to the goal G? And which path? Pause and work it through. I'll wait. Here's the walk. Pop S at 0. That sets G of a 2-1 and G of B to 5. The smallest is A. So pop A, G of C becomes 2, G of D becomes 5. Smallest now is C at 2. Pop it, and the goal G gets cost 3. G at 3 is now the cheapest in the queue, so we pop it and stop. The answer is cost 3, along S, A, C, G, 3 light edges. The tempting shortcut through B would have cost 10, and uniform cost search never even bothered to expand it. If you got 3, you've truly got this. Trap 1. Depth first search is not optimal, ever, in general. The first goal it stumbles into may be far deeper and far more expensive than a shallow one nearby. It stops at any solution, not the best. Trap 2 breadth first search doesn't usually run out of time first. It runs out of memory. An entire frontier level sits in the queue, order B to the D. That exponential space is its real wall. Trap 3. Uniform cost search assumes every step cost is non-negative. Slip in a negative edge, and settling a node early can lock in a cost that a later shortcut would have beaten. For negatives, you'd reach for a different algorithm. And trap 4. The one people get backwards. Iterative deepening's re-expansion is not a disaster. The deepest level dwarfs everything above it. So redoing the shallow nodes costs only a small constant factor. The time stays order B to the D. Let's bring it home. Breadth first search runs a first in first out queue, level by level. It's complete and optimal for equal costs. but pays with B to the D time and, worse, B to the D memory. Depth first search runs a last in first out stack, plunging deep. Its memory is a lovely order B times, but it's neither optimal nor, without a limit, complete. Uniform cost search runs a priority queue, keyed by path cost G of n. It expands the cheapest node first, and it's optimal for any non-negative costs. Dijkstra's algorithm in search clothing and iterative deepening gives you depth first's memory with breadth first's completeness by sweeping the depth limit outward, and the rework costs almost nothing. 4 blind strategies, no map required. Choose by asking, equal costs or weighted, and how much memory can you spare?